So this begins our unit on thermal physics and thermodynamics. In this first video, we'll begin by introducing the concept of temperature. From there, we'll take a look at the thermal expansion of materials, a property of materials that results from changes in temperature. And finally, we're going to end today's lesson by introducing or hopefully reviewing the macroscopic properties of ideal gases. I'm hoping that many of you will have learned something about ideal gases in a chemistry course that you might have previously taken. And I almost forgot. Okay, something else you'll learn in today's lecture. Okay, the physics behind opening a tightly lidded jar, even when you're not an octopus. Now, the word temperature is certainly not new to your vocabulary. You've known about and used this word since you've been a small child, I'm sure. And I'm betting that you all have a pretty good intuitive understanding of the concept of temperature as well. You may think of temperature as a measure of how hot or cold an object is. Okay, this understanding of temperature is based on your senses, and while it's not wrong, okay, it is limited and doesn't provide a good understanding of what causes temperature. That is, what causes an object to be hot or cold. Using your senses to measure temperature can lead to inaccuracies, as the following example will illustrate. So let's see what Theo the thermometer has to say here. And let's consider, what happens, for example, when you stick your hand inside of a hot oven to remove some food. If your hand comes in contact with nothing but the air inside of the oven, no problem. Okay, but if your hand were to touch the metal oven rack or the metal sides of the oven, ouch. Okay, you've just got yourself burned. Why is it that the metal rack feels hotter than the air inside when both are at the same temperature? Okay, so you see here how using your senses, okay, to determine the hotness or coldness of an object does not provide a reliable, measure of temperature. So now that we've talked about forms of energy, you've talked about this in your mechanics class, and you have a very good understanding of what kinetic energy is, we're now in a position to provide a better definition of temperature, one that is not based strictly upon your senses. Now, the true meaning of temperature is rooted in the kinetic theory of matter. So before we can really understand what temperature is all about, we need to understand this basic theory of matter. So the basic premise of the kinetic theory of matter is that all matter consists of tiny particles, usually atoms or molecules, that are in constant motion. So if you take a look at the picture on the left-hand portion of the screen, you can see that inside this container we have a bunch of gas molecules, gas particles. And that these red arrows you see for each of the gas particles represent velocity vectors, showing that they are all in motion. If you take a look at the velocity vectors a little closer, you'll notice that all of these particles are moving randomly in different directions. And this is one of the fundamental principles of the kinetic theory of matter. Not only are the particles in constant motion, they're not moving in any preferential direction. They're moving randomly. So this idea that all particles move randomly in three-dimensional space is true really for all states of matter, whether we're talking about a solid, a liquid, or a gas. That for all matter, the particles that make up that matter are in constant random motion. And remembering back to our definition of kinetic energy as being motional energy, to say that all particles making up matter are in motion is synonymous with saying that, okay, these particles possess kinetic energy. So how do the states of matter differ from one another from a microscopic perspective? So if we could shrink down to the level of individual particles, whether atoms, ions, or molecules, how are solids different from liquids, different from gases? We can most easily distinguish the states of matter by considering the following properties. That is, the space between individual particles. Okay, is there a lot of space or little space? The strength or magnitude of the attractive forces between the particles, and the way in which the particles themselves move. When we talk about the motion of particles, we're talking about not only are they moving fast or slow, but what type of motional freedom do they have? Can these particles, can they vibrate? Okay, can they rotate? Can they translate? So let's start by taking a look at the case of solids. Okay, we would say that on average, okay, solid particles are quite close together. The particle spacing is small. This would suggest, when we take a look at the electrostatic or Coulomb force, that the attractive force between two solid particles is quite large. Okay, that strong attractive force keeps them pretty close together. When we talk about the motion of solid particles are moving quite slowly, at least in comparison to liquids or gases. And when we look at the motional freedom of these particles can vibrate about relatively fixed positions in 3 dimensions, but these particles don't ever travel great distance. They can't actually leave each other, nor can they actually start to rotate around each other. When it comes to liquids, okay, liquids represent somewhat of an intermediate state. Okay, compared to solids, there's a little bit more space between particles. Okay, the attractive forces are not quite so strong, and because there's a little more space and the attractive force is not quite so strong, this means that the particles can move a little bit faster, and the particles can start to move a little bit away from each other, enough to actually rotate around each other. It's this rotational freedom that gives liquids this characteristic ability to flow. And finally, when we look at gases, okay, we would say that on average the spacing between gas particles is quite large, which suggests that the attractive forces between gas particles is very, very small. This means that gases, on average, the particles are moving quite fast in comparison to solids and liquids, and that these particles have much more motional freedom. They can vibrate, they can rotate, and unlike in the case of liquids or solids, gas particles can actually translate, which means that they can leave each other for good. They can completely move away from each other. Okay, this means that gases can move from one side of the container to the other. And as we see, gases have this ability to expand to fill their containers. You see here in the case of liquids that because the particles can't actually leave each other, okay, they maintain a fixed volume. And this is why we say liquids are fairly incompressible, just like in the case of solids. Now that we're equipped with a basic understanding of kinetic molecular theory, this idea that all matter consists of tiny particles that are in constant motion, we can now return to this idea of temperature and explain what temperature really means on a microscopic level. So a better definition of temperature goes like this. We define temperature to be a measure of the average kinetic energy of the particles that make up an object. And in layman's terms, we're really saying that temperature measures how fast the molecules are moving on average. So
Remember when we talked about kinetic energy, okay, kinetic energy is motional energy. It's a measure of energy of motion. And when we say an object is hot, okay, we're saying that on average, those particles in the object are moving quite fast. Contrary to a cold object, where we would say that on average, the particles in that cold object are not moving nearly so fast. It's important we use this idea of average because even in a very cold object, there will be a few molecules moving relatively fast. And conversely, in a very hot object, there will be some molecules that may be moving quite slowly. So on average, though, we can say that a hot object has fast moving molecules and a cold object on average has much slower moving molecules. Now we'll take a look at a demonstration, and this is a nice way to see first of all that the kinetic theory is alive and well. Okay, we can actually see molecular motion or see the results of it, and it will also show us, we'll be able to see the difference between a hot object and a cold object and its effect upon molecular motion.
All right, so folks, what we have here is we have 2 beakers full of water, and as you can see here, we've got hot water in this beaker and we've got cold water in this beaker. Now, according to kinetic molecular theory, although we cannot see it, okay, we know that the molecules of water in this beaker full of hot water should be moving on average much faster than the molecules of water in the cold beaker. Now, like I say, we can't see that with our naked eye, but kinetic theory tells us that is what should be happening. But one thing we can do to try to see this, to see that temperature is really a measure of the kinetic energy of the particles in the medium, to see that temperature measures molecular motion, what we're going to do is we're going to take some food coloring here, some food coloring particles, because those molecules we can see, and I'm going to drop them both in. I'm going to start over here with the cold water. I'm going to try to very carefully put a drop right on the surface here. Okay, and then I'm going to put another drop right on the surface of the hot water here. Okay, and we're going to see about how fast these molecules are moving. Okay, so when we make a comparison, we can see that these food coloring molecules, okay, their motion tells us something about the water molecules. And as you can see here, the fact that the red food coloring molecules are spreading much faster in the hot water tells us that the molecules in the hot water, the water molecules, are moving much faster on average. That is what's causing the spreading. That's what's causing this greater rate of diffusion. Okay, so you can nicely verify kinetic molecular theory by taking a look at what's happening with the food coloring molecules. Now, eventually, even these food coloring molecules in the cold water, they will be evenly distributed throughout. Okay, it's just that it's going to take much longer, suggesting that on average, the water molecules are moving much slower here for the cold water. It's going to take much longer for those food coloring molecules to spread out throughout the container.
In this slide, we'll take a look at a conceptual problem that will help to illustrate the difference between average energy and total energy, an important distinction. Okay, in this problem, we're told that the typical temperature from a 4th of July sparkler is on the order of 2,000 degrees Celsius. Okay, so why then doesn't it hurt when sparks from the sparkler land on your skin? Well, here we can see from our knowledge of the definition of temperature that while temperature is high and the average kinetic energy per molecule is large, the total energy transferred to the skin is quite small. And it's the total energy that causes the problem, that causes the pain, not the average kinetic energy. So, in this case, you can see that a small number of particles moving quite fast may make for a high average kinetic energy, but the small number of particles means that the total energy of the system is not large at all, in which case the total energy that could be transferred to your body, okay, will not be large. So let's talk about this important concept called thermal equilibrium. We'll start out by giving a definition for what it means for two objects to be in thermal equilibrium with each other. Thermal equilibrium is that situation in which the net transfer of energy ceases for two objects in thermal contact. And this brings us to what we call the zeroth law of thermodynamics. Okay, zeroth because it came after the first and second law, which we'll talk about later. This law tells us that if objects A and B are in thermal equilibrium with a third object C, then objects A and B are also in thermal equilibrium with each other. So if we take a look at the schematic here, this nicely illustrates the law. So if object A is in thermal equilibrium with object C and object B is in thermal equilibrium with object C, then this implies that A and B must be in thermal equilibrium with each other. So thinking about that, okay, what are the implications about temperature if, okay, object C just so happens to be a thermometer? What does that imply about the temperatures of A and B? Well, let's solicit a little bit of help from our smart thermometer here, Theo. See what he has to say. Well, this would imply that if, okay, these two objects are in thermal equilibrium with a third object, which we now call a thermometer, and according to the zeroth law, they must be in thermal equilibrium with each other. Okay, this would imply that these two objects, A and B, must be at the same temperature. So it turns out that when the temperature of samples of matter changes, so do many properties of that sample of matter. So when we speak about a thermometric property, we're really talking about any property of matter that changes with temperature. And there are many examples of this. We will look at a few of them. Okay, starting with, okay, the volume of a liquid or gas. And we'll also take a look at how these thermometric properties can be applied, okay, how we see them used in various technologies in society. So an obvious example of this would be a mercury or alcohol thermometer, okay, the typical thermometer that you use in a laboratory. You know that that column of liquid, whether mercury or alcohol, will change with temperature. Okay, as the temperature increases, there's some thermal expansion, and the volume, okay, of that liquid increases as well, causing the mercury or alcohol to rise. Here's a case where you can see what the effect of, okay, a change in temperature on a gas. And you see here that as we cool that balloon down with some liquid nitrogen, look at what happens to the volume of it. It decreases greatly, enough to actually cause a helium balloon to sink. Okay, and then when the temperature rises, you can see here that the balloon will rise as well as the volume increases. The dimensions of a solid in general. Okay, we talk about thermal expansion, and in the next slide I will show you an example of a bimetallic strip, a common technology that's used in thermostats, for example. So in this video, you'll see a bimetallic coil react to heat here, really in the form of a lighter. These bimetallic coils are in thermostats, and you can see how they expand. You really have two dissimilar metals that are welded together that will expand when heated and contract when cooled. So let's quickly finish our discussion of the bimetallic strip or coil and see how it can be used in a thermostat. So remember that a bimetallic strip or coil is simply two dissimilar metals, two different metals that are welded together that will expand by different amounts when heated. And because they're welded together, this causes a strip to bend either right or left, okay, when it is heated, okay, or cooled. The bimetallic coil is just a longer strip that is more sensitive to changes of length with temperature. But you can see here in this illustration that the bimetallic strip or coil is placed inside the thermostat, and for a given temperature, the strip or coil will be in a certain position. And you can see here how when it's in the on position, it is making electrical contact with, let's say, a heater in one season or an air conditioner in another season. So in most thermostats, you have really two electrical contacts. You have one for the heater, one for the air conditioner. And you can see that, you know, at a given temperature that if we're talking about a heater, for example, when the temperature of the room gets high enough, it will cause a strip to bend enough, okay, to stop the electrical contact with the heater and turn off the heater. So you can see how this is a nice technology, okay, the fact that the dimensions of a solid will change. And we will talk more about thermal expansion, okay, in this video in a little bit. The color of an object. So I say here are some examples, you know, baby thermometers, mood rings, thermographic paper. Well, you know, you've seen examples of matter that when heated will experience a color change. Okay, you may see that when you heat a metal, typically at a low temperature, it's going to glow in the red frequency range, whereas when you can get that piece of metal high enough, okay, it's going to turn more into blue, okay, sending off more wavelengths of blue light. You've probably seen these baby thermometers, which you know how hard it is to stick a medical thermometer in the mouth of a child. Okay, these baby thermometers you can press on their forehead and they will change colors, okay, with various temperatures. I will show you an example of something that was quite popular when I was a kid. These are called mood rings, and you can see that as the temperature of your hand, your finger changed throughout the day, so did the colors of the ring. Yes, everybody who was cool had one. Okay, back in the day, that was in the early 70s. Kind of hard to believe, huh? Mood rings. The electrical resistance of a conductor is also a thermometric property. It turns out that electrical resistance varies greatly with temperature, in which case some of your most sensitive, most precise thermometers are made using this property. Okay, the example we looked at above for a thermometer was using the expansion or change in volume of a liquid with temperature. The thermistor, the change in electrical resistance, is an even more sensitive thermometric property. And here's an example of a thermistor. In fact, we will be doing a lab on thermal expansion in Physics 102 that makes use of a thermistor to be able to measure, sensitively measure changes in temperature, much better than a mercury or alcohol thermometer ever could. The vapor pressure of a confined gas at a constant volume. And this is the constant volume gas thermometer, and here's a schematic of one. You can see here that we have a container which has a fixed volume. Inside that container is a gas, and you will see that when that gas is heated, we're not allowing the volume to change like in the case of the mercury alcohol thermometer, but it does cause a pressure increase, which can be recorded. So Turns out that, okay, gases are sensitive, their pressure is sensitive to being changed with changes in temperature. Okay, and lastly, we'll take a look at the volume of gas at constant pressure. This is not a whole lot different than we looked at in this first example here, but we will take a look at a technology which is quite important to us in our daily lives, unless you drive an electric vehicle, and that is the work done, okay, by the piston in the cylinder of an internal combustion engine. Okay, you can see here that inside of that cylinder we have a gas which we allow to combust, and when that gas combusts, the volume of it changes greatly, okay, with that increase in temperature. So here we have a fairly constant pressure, right, because that gas can actually move against this piston, which is providing some sort of resistance force, but a fairly constant pressure, not exactly. Okay, but you can see that as the gas is ignited and the temperature increases greatly, so does the volume of that gas. So, have you ever built a thermometer before? This used to be a very common elementary school project. I say you're building a mercury alcohol thermometer. I don't think they're going to let kids build a mercury thermometer today. Okay, not like the good old days when I was a kid and they would let you play with mercury. Okay, nobody was really that aware of the dangers of it. Okay, and that could explain a lot of perhaps my mental problems. So let's think about if you want to build an alcohol thermometer, or you could use some other liquid, and you get a tube closed off at one end. Okay, put some food coloring or whatever in your liquid so you can see it. And then to calibrate your thermometer, okay, start by sticking it in some ice water, okay, which you know is going to be your low end of the temperature scale. In Celsius, we'll call that 0 degrees Celsius. Okay, so when you put that in there, you can see that this is going to cause the column to drop when it cools from room temperature down to 0 degrees Celsius. Put a little mark on the outside of your tube at that point. Okay, that is 1 point for calibration. You're then going to take your thermometer, and now you're going to look at the other extreme. You're going to place it in some boiling water, which you know is going to be at least in the Celsius scale, at 100 degrees Celsius. So go ahead and put it in there, and you will see that it is going to, that column is going to rise up. As we said, this is a thermometric property that that column of fluid is going to expand. Okay, its volume will increase with temperature. Put another mark, okay, at that point. Now you have the two marks on your tube, which you're going to call a thermometer, and divide those two marks into 100 equal spaces, okay, 100 equal divisions, and now you have yourself a Celsius thermometer. And the best thermometers, the most accurate ones you can buy that you pay a lot of money for, okay, are actually calibrated this way. Okay, the cheap ones will just be, they'll just stick a scale on the outside, paste it on there, but your better ones are actually calibrated with these two temperatures in mind. Okay, so you can know exactly where the 0 point is on your temperature scale, and you can know where the boiling point of water is on your temperature scale. So we're now going to talk about temperature scales, and in order to do so, I'm going to tell you a story. Okay, or maybe stories. Sorry. So one day, many years ago, I went to my favorite Mexican restaurant and I ordered a hot tamale. The waitress brought me a tamale that must have come straight from the refrigerator. It was at 10 degrees Celsius. I sent it back and told her that I wanted a hot tamale. in fact, a tamale that was twice as hot. What should she bring me? What should his temperature be? So here, make a mental note, okay, as to how you would answer this question. Well, the cook was obviously not happy that I was complaining, and rather than spitting in my food, he sent the tamale back to my table that must have come straight from the freezer. When I pulled out my thermometer, okay, which I always carry with me, it measured 0 degrees Celsius. Again, I sent it back and told her that I wanted a hot tamale, okay, in fact, one that is twice as hot. What should she bring me? Okay, what should his temperature be? Okay, how many of you said 0 degrees Celsius? I'm sure that some of you did, in which case I'm going to have to tell you another story. So in my mid-20s, I moved to Italy. And what many people don't know is that before teaching physics, I worked in a small village in Italy. Any guess as to what I did there? Okay, well, I'm sure that, okay, the first thing that came to many of your minds was that I was a tailor. And if so, you'd be correct. In my shop, I would measure the heights of all my customers against this stick, which was firmly fastened to the wall of my shop. Now, this stick need not extend all the way to the floor or to the ceiling, since my shortest and tallest customers would always fall within the extremities of this stick. And all tailors in this region of the country use the same method of measuring their customers, so they could communicate meaningfully with each other about the relative heights of their customers, provided that the measuring sticks in each shop were fastened the same distance above the absolute 0 of height. And by the way, it just so happened that the distance to the floor, okay, that is the absolute 0 of height, was 273 notches, the same size notches, in fact, as on the stick itself. Now, then one day, okay, the most amazing thing happened. A very short woman came into my shop, and when she stood against the stick, okay, the top of her head was exactly coincided, okay, with the bottom, the 0 mark of the stick. As I was taking her 0 reading, she commented to me that she had a brother, okay, who was exactly twice her height. So my question for you is, what is the height of her brother? Okay, and let me go back and ask the question, what is the temperature of the twice as hot tamale? Okay, that is the one that came directly out of the freezer. Okay, well, you see that if you said 0, okay, for the twice as hot tamale, you would be incorrect in the same way, okay, that the brother who is twice as tall is this woman who measured 0 on the measuring stick, okay, he does not have a height of 0. So you can see the problem with using, okay, the Celsius scale as opposed to an absolute temperature scale, which we'll talk about in the next slide. So in this slide, we will formally talk about this concept that we call absolute 0. We can think of absolute 0 as a theoretical lower limit of temperature. Now, remember what we say temperature is, right? Temperature is a measure of the average kinetic energy of the particles that make up an object. So temperature, in a sense, is a measure of particle motion. So as particle motion slows down, as those particles lose speed and lose kinetic energy, their temperature decreases. So in this sense, it would make sense to then define the 0 point of temperature as being that point at which a particle had no motion. It had no kinetic energy. Okay, the temperature at which molecular motion ceases. Okay, now if we ask ourselves, what would a sample of matter at absolute zero look like? Well, we said that the particles would not be moving, but this would also imply that a sample of matter at absolute zero would have no pressure as well. Think about when we talked about pressure, we said, well, pressure is a measure of force per unit area. If the particles in the container did not move, they could not collide with the walls of the container. They could not exert a force on the container walls. Therefore, they could not exert any kind of pressure. So in addition to having no motion at absolute zero, okay, macroscopically, we could say that there would be no pressure to a sample of matter either. Now, I say here that this is a classical result only because, okay, in the world of quantum mechanics predicts something that we call a 0 point energy, which is really due to the quantum fluctuations that result from something called the uncertainty principle. We'll talk more about this in Physics 103. But the uncertainty principle says that you can never say that a particle would have no kinetic energy or no motion, because doing so, okay, would allow you to definitively say what, okay, the energy state or, okay, position, motion of a particle would be at a precise time. And this would directly violate a very fundamental principle of quantum mechanics. We cannot know the exact position or the exact energy of a particle precisely. So we cannot say that a particle has no motion definitively, okay, from a quantum mechanical perspective, although classically we can do that. Last thing we'll put up on the slide is a statement of the third law of thermodynamics, which says that it is impossible for any real object to ever reach a temperature of absolute zero. And we're going to really understand this, it would help to understand the second law of thermodynamics, which we will talk in great detail, okay, in a little over a week. The second law tells us that heat spontaneously flows, thermal energy will spontaneously flow from an object at a high temperature to one at a low temperature, but never the reverse. So if you think about how your freezer typically works, in order to bring your freezer compartment to a certain temperature, you must actually place that compartment in contact with an object at a lower temperature in order for heat to transfer out of it. So this would imply, in a sense, that in order to bring an object to absolute zero, you would have to put that object in contact with another object that was actually below absolute zero, which would be a physical impossibility if we say that absolute zero is really that state at which particles have no motion. Okay, there's no concept of a particle having negative motion. Right, so there are really three common temperature scales that we will come across in this class, in this course, and in this country that you should have some familiarity with. Okay, Theo is going to help us out here. So this is the Fahrenheit temperature scale, the Celsius temperature scale, and of course the one we're talking about here, the Kelvin or absolute temperature scale. And all of these scales are based upon the normal freezing point of water and normal boiling point of water. Okay, that's how these scales are calibrated. Okay, that's what they're based on. So you need to recognize these calibration temperatures, as well as you need to have some ability to convert from one temperature scale to another. As you know very well with units, very often you've got a problem you have to solve, and in order to do so, you have to be able to convert from one unit system to another. Same thing goes with temperature. So look, the Fahrenheit scale, as we know, this is a bad British unit, and it makes little sense. As you know, the reason that we have the the unit system that we do, the SI unit system, is because all of the units are related to each other by powers of 10. But on the Fahrenheit scale, you see that the normal freezing point of water is 32 degrees Fahrenheit, whereas the normal boiling point is 212. Okay, there's very little relationship, between these 2 points, or I should say one that makes a lot of sense. So the normal freezing point of water on the Fahrenheit scale is 32 degrees, on the Celsius scale is 0 degrees, and on the Kelvin scale it is 273. We don't actually say degrees, we just say 273 Kelvin. When we look at the boiling point on the Fahrenheit scale, it's 212 degrees Fahrenheit. On the Celsius scale is 100 degrees Celsius. And on the Kelvin scale, it's 373 Kelvin. So when it comes to absolute zero, that temperature at which molecular motion would cease, well, on the Fahrenheit scale, the value is negative 460 degrees Fahrenheit. On the Celsius scale, it's negative 273 degrees Celsius. But, on our absolute temperature scale, it's 0. And remember, absolute temperature, we're saying, should measure particle motion. So it makes sense that when particles have no motion, their temperature is 0. These conversion expressions that allow you to go from one temperature scale to another, we can state them in many ways. I'll give them to you like this, that the Fahrenheit temperature is equal to this fraction 9/5 times the Celsius temperature, and then we have to add in this 32 degrees because they have a different starting point, right? Notice at the Fahrenheit scale, the starting point for the freezing point of water is 32 degrees above what it is on the Celsius scale. So basically, it turns out that a Fahrenheit degree is related to a Celsius degree by this factor of 9/5. So you can use this expression to go from Fahrenheit to Celsius, or from Celsius to Fahrenheit. Just means you have to solve it, for Celsius temperature, which can be done. When it comes to the Kelvin temperature scale, you'll notice here that a Kelvin and a Celsius degree have exactly the same size. The only difference is where they start. So the Kelvin scale is very closely related to the Celsius scale, but they have different starting points. So we have to add in this factor of 273, due to their different starting points. So in the next couple of slides, you will hopefully learn something important about the relationship between the Celsius scale and the Kelvin scale, by taking a look at this example. So here we're told that an experiment is conducted whereby a gas in a container of constant volume is heated from 0 degrees Celsius to 100 degrees Celsius. We're asked to sketch what the relationship between gas pressure and temperature would look like, where temperature is measured in degrees Celsius. Now, obviously, you didn't actually conduct this experiment, so you're just going to have to take my word here. But if you were to conduct a controlled experiment, keeping the amount of gas and the volume of gas fixed, where you changed the temperature of the gas and saw how that affected the pressure, what you would discover is that there is a linear relationship between pressure and temperature. And you would, if you were actually to plot some points, in this region here from 0 degrees Celsius to 100 degrees Celsius, probably what your Celsius thermometer could measure, you would find that this portion of your graph would be linear. You could then extrapolate your data, that is, interpret or read beyond the range of data you collected. And when you extrapolated this line, you would find out that it would cross your temperature axis, okay, over here at a point corresponding to negative 273, okay, 0.16 degrees Celsius. So, like I say, you didn't actually plot these points, but this is the answer. This is what a graph would look like if you were to do that. And the next question says, well, again, sketch the graph, but this time on a set of axes where temperature is measured, not in Celsius, but now, okay, in absolute temperature units or Kelvin. And again, you didn't conduct this, so, okay, what you will see here, and we will discuss this on the next slide, okay, where we have room to answer these next questions. Okay, when you look at your graph, you say, it looks like it has a lot in common with the graph, okay, on the left, okay, but it looks like the graph has been shifted horizontally, okay, even though it looks identical when we look at the pressure axis in the vertical direction. Right, so let's finish up this problem, and you'll notice I kept the graphs here at the bottom of this slide. So the next question asks us to identify the temperature axis intercept for the graph where the temperature was measured in 1st degrees Celsius. So notice here that, okay, when measured in degrees Celsius, okay, the temperature axis intercept is minus 273 degrees Celsius. Okay, this is what absolute zero is in units of degrees Celsius. Okay, but if we want to find the temperature axis intercept, okay, when we're measuring temperature in Kelvin temperature units, we see here that it is actually 0 Kelvin. And remember, this is when it comes to what temperature means, what we now think temperature means, temperature being a measure of particle motion, the absolute temperature scale is what we would need to use, okay, to be able to measure that, okay, to be able to measure a particle's motion. It wouldn't make sense to use a Celsius scale to use a value of 0 for particle motion when clearly a particle was moving at a temperature of 0 degrees Celsius. In terms of the shape of the graphs, how are they similar to one another? Well, you'll notice that they have exactly the same slope, and what that tells you is that, you know, a 1 degree Celsius has the same value as 1 degree Kelvin. Okay, the size of a Celsius degree is the same as the size of a Kelvin unit. Remember, we don't say degree. How are these graphs different from one another? Well, they have different horizontal axis intercepts, right? They intercept, okay, the horizontal axis, the temperature axis at different points. Okay, and finally, how does the size of a degree on the Celsius scale compare to the size of a degree on the absolute temperature scale? They must be exactly the same, okay? And the fact that the slopes of the graphs are the same would imply that, okay, the size of 1 unit of temperature on each scale would be the same as well. So in this slide, we will gain some practice converting temperature units, okay, from one temperature scale to another. And in this problem, we're told that normal human body temperature is 98.6 degrees Fahrenheit. Now, chances are that if you grew up in this country, this is a number and unit that you're very familiar with. But in this question, we're asked to make a conversion between Fahrenheit and degrees Celsius. In other words, what is a normal human body temperature in Celsius temperature units on the Celsius scale? Certainly, if you were born in Europe or South America, you would most likely be familiar with the answer to this question. You would know that. But either way, we're going to do the conversion and be able to determine that answer. Hopefully, if you were born in this country and you don't know that answer, you now will, and it is a useful number to know. So in order to do this, we will revisit this conversion that was given to you a couple slides ago. And you'll notice here that this conversion, the way it's expressed, it converts Celsius units into Fahrenheit, but in this problem we're asked to do the opposite. Okay, we need to convert a Fahrenheit temperature into Celsius temperature, which means we have to solve this equation for degrees Celsius. And in order to do that, we'll do a little bit of algebra. We'll subtract 32 from both sides and multiply both sides by 5/9. And just be careful when you do that. Make sure that when you multiply both sides by 5/9, you actually multiply both sides by 5/9. That is, you include parentheses. That is a very common mistake people make here. When you plug in the numbers, you come up with a body temperature of 37 degrees Celsius. We're next asked to convert that temperature into absolute temperature units, okay, Kelvin units on the absolute temperature scale. And remember that a Celsius degree and a Kelvin degree have the same size. The only difference is the starting point on the scale. So here, okay, the Kelvin temperature will be equal to the Celsius temperature, but then we're going to add 273 Kelvin temperature units in order to shift our 0 point here. When we plug in our numbers, okay, we come up with a Kelvin temperature of 310 Kelvin. So hey, just a piece of advice. You know, if you're ever feeling sick, feel like you've got a fever and you're just craving a little bit of sympathy from your significant other, a surefire method for getting that sympathy, for getting that little bit of extra attention is to state your temperature in Kelvin temperature units. Okay, it works every time. So we are now going to revisit one of the thermometric properties that we introduced in an earlier slide. One that is important in society, okay, one that routinely affects us, okay, one that we will explore on a quantitative level. Okay, and that thermometric property is, okay, the thermal expansion of solids and liquids. Okay, the idea that as you heat up a solid or liquid, as the temperature of that solid or liquid increases, it takes up more space. Now, certainly when we talk about this expansion, we can talk about an expansion in 1 dimensions, in 2 dimensions, or three-dimensional expansion. What is the underlying root cause of this thermal expansion? Why is it that materials, when their temperature increases, take up more space? Well, we'll look at a very simple model, but thinking about our definition of temperature, as the temperature of a sample of matter increases, the average kinetic energy of the particles that make up that sample of matter also increases. And when we think about these particles having more motion, these particles all having connections or attractions to each other, okay, at least for the solid state, the vibrational motion of these particles, we can say that the amplitude of vibration is going to increase. Okay, therefore, these particles will end up taking up more space. A very nice way to think of this is to think about these particles, think about these interparticle forces as being a connection, okay, between particles by springs. And these springs can simulate this interparticle force, this interparticle attraction. Of course, you know, what complicates things is that when we looked at simple harmonic motion, for example, we looked at, you know, a single spring, and now we're talking about a particle being connected by multiple springs. So while the actual amplitude of vibration of any individual particle is complicated, okay, by this three-dimensional motion rather than one-dimensional motion, hopefully you can still at least agree that the amplitude of vibration is going to increase, okay, as these particles gain kinetic energy, as they gain speed, as they move faster, okay, their amplitude of vibration will increase, which will result in the fact that they will end up taking up more space. Now, on a molecular level, you cannot see thermal expansion of these individual particles. But in the next slide, I'll demonstrate for you, okay, the noticeable effect of what happens when you are looking at a conglomerate of particles. When you look at enough particles, okay, you can see the macroscopic effect that a change in temperature will have on the amount of space they occupy.
All right, folks, this is the classic ball and ring demonstration. Notice in my right hand I have a copper ball, my left hand a copper ring. And you'll notice that the ball fits nicely through the ring. Now, we talked about thermal energy or heat energy being a form of microscopic kinetic energy. That is, the kinetic energy associated with the random motion of the particles in an object. And right now, the copper atoms in this ball are moving about randomly. They have a certain amount of microscopic kinetic energy associated with them. But if I were to take this copper ball and add some heat to it, as we can do with this Bunsen burner flame, we will be increasing the kinetic energy of those copper atoms. And when those copper atoms increase their kinetic energy, they're going to take up more space. So let's see this in action. I'm going to put the copper ball in the flame here, add some thermal energy. Okay, those copper atoms are going to be moving faster. Now, certainly you can't see the motion of those copper atoms. You can't even see the copper atoms, but you will be able to see the effect of their increased motion. Okay, because when I take the copper ball out of the Bunsen burner flame, you'll notice that it no longer fits through the ring. Those copper atoms are moving about faster, causing this ball to be a little bit bigger, to occupy a little bit more space. So, once again, thermal energy is a form of microscopic kinetic energy associated with the random motion of the particles in an object.
So in this slide, we will state these empirical equations that will tell you how much expansion you will get in a sample of matter. And you'll notice here that we can talk about a one-dimensional expansion. Okay, when we're considering a one-dimensional object, we can talk about expansion in 2 dimensions. Okay, for example, an area expansion if we're talking about a thin object like a plate. Or we can talk about 3-dimensional volume expansion. And I would say this, that you may say, well, why talk about one-dimensional expansion? There's no such thing as a one-dimensional object. Okay, but very often we are only interested in the expansion in 1 dimension, in which case we're not worried about the expansion in other dimensions. We don't have to treat the full volume expansion. For example, if you're building a bridge and you want to know how much that a girder in that bridge is going to expand in length, okay, that's of primary concern when you're trying to build a bridge is structurally stable. How much it expands in thickness and depth may not be of concern to you, in which case you're only going to focus on the one-dimensional or linear expansion. So these equations are empirical, okay, but I hope that they will make sense to you when you think about it. What sort of things will affect how much an object will expand in 1 dimension when its temperature changes? Well, if you think about it, I think certainly this equation should make sense to you. Okay, the amount of expansion, that is the change in length of the object, well, certainly it should depend upon the type of material you're talking about. And this thing alpha is what we call a coefficient of linear expansion. It depends upon the material type. Some materials will expand more than other materials for the same change in temperature. Okay, I think that this should make sense as well. Okay, should the change in length of an object depend upon the initial length? Certainly. The longer the object is to start out with, the more molecules it has, okay, the greater its change in length will be for a given temperature change. Okay, and think about it. A 1,000-meter bridge is going to experience a bigger change in length with a 5 degrees Celsius change in temperature than a 1-meter long bridge. And finally, of course, the amount of temperature change is going to affect the change in length. We would expect that the greater the temperature change, the greater the length change as well. So delta T measures the change in temperature. When it comes to a two-dimensional area expansion, we will actually show that this two-dimensional coefficient is just twice the linear coefficient. But in the same way, A naught represents the initial area of the object. Okay, of course, delta T, the change in temperature. And for a three-dimensional volume expansion, okay, here 3 times alpha, that is 3 times the average coefficient of linear expansion, V naught, the initial volume of the object. So these thermal expansion coefficients are determined empirically, that is through experiments. Talk a little more about that in a second. And you can see here some typical examples for coefficients of linear expansion as well as for coefficients of volume expansion. Okay, I want to point out here on the previous slide we said that the coefficient of volume expansion we're calling here beta is really equal to 3 times the coefficient of linear expansion. You can see that that is indeed the case. For aluminum, for example, the linear expansion coefficient is 25 times 10 to the minus 6, but the volume coefficient is 3 times that, okay, for 75. This pattern typically holds here for glass. The linear expansion coefficient is 9 times 10 to the negative 6, whereas for the three-dimensional volume coefficient, it's 3 times that, or 27 times 10 to the minus 6. It's also worth noting here that different materials may have very similar expansion coefficients. So you'll notice here that iron and steel have an expansion coefficient that is very similar to that of concrete. Okay. Like I said, these expansion coefficients are determined empirically through experiment, and one of the labs that we do in Physics 102 is kind of what's being illustrated in this, this animated GIF here, that you heat up a piece of metal and you can, with a sensitive instrument, measure its change in length. Okay, so knowing, the initial length, the temperature change, which we use a thermistor for to be able to accurately measure the temperature change. Okay, initial length, change in temperature, and change in length. Given those 3 quantities, you can then measure what this expansion coefficient is. All right, so we said a couple slides ago that the coefficient of area expansion is just twice the coefficient of linear expansion. And in this slide, we're asked to actually show that. So let's consider the rectangular plate that is shown here, in the figure, that has initial area A naught. Okay, it has an initial length L naught, initial width W naught. And we're told that if the temperature increases by an amount delta T, we want to show that the increase in area, that would be this L-shaped strip here, the change in area, we want to show that it would be given by this expression, 2 times the coefficient of linear expansion times the initial area times delta T. All right, and so let's try to show this using this empirical relationship that we have for the linear expansion of a material. So let's start by saying, well, our total area after we've increased its temperature is going to be our initial area A naught, plus whatever that change in area is. And when you look at this, our object starts out as let's say a thin plate. okay, which is rectangular, it ends up as a thin plate, which is rectangular, okay, but where the length and the width have increased, okay, by a certain amount. So the area we end up with, this larger rectangle, is just its length times width. So we'll say its length L naught plus its change in length due to the expansion, okay, times its width, its initial width W naught before the temperature change, okay, and after the temperature change, the width is increased by an amount delta W. So we're just going to start with this expression here, and using our definition of, okay, our empirical relationship describing linear expansion, okay, and making some substitutions here, we will say that delta L, the change in length, is just given by this expression here, is equal to alpha times the initial length L naught times the change in temperature. We'll do the same for the width here. The change in width is just alpha times the initial width times the change in temperature. Now we're just going to do some algebra here. We've got two binomials that we're going to multiply together. So when we multiply our two binomials together, we're going to end up with these four terms, right? L naught times omega naught, that's multiplying our first terms. Okay, our inner terms, alpha L naught delta T omega naught, multiplying this. Our outer terms, okay, alpha omega naught delta T times the outer term in our first binomial L naught. And then multiplying our last terms, this term, okay, and this term here, we get, alpha squared L naught omega naught delta T squared. Now, here's where we will, factor out an L naught omega naught, which from all of these terms, that's a common factor. All that good algebra that you once learned is, coming in handy here, in this problem at least. And we are going to make an approximation here that those coefficients of expansion were small numbers. Remember, in MKS units, they were on the order of 10 to the minus 6, okay, MKS units. So when you take a small number and you square it, you get a really small number. So this is where we're going to say that we will neglect the higher order terms, the squared term, okay, because it will be very, very small. So, and if you're a little bit confused by this, take a number, okay, like 10 to the minus 6, square it, you get a number 10 to the minus 12, and you can see that 10 to the minus 12th is insignificant in comparison to 10 to the minus 6. So this is an approximation that we very often make in physics to simplify our calculations. So with this approximation here, okay, our equation reduces to, here, just want to point out L naught omega naught, that is just A naught, that is our initial area. So we're going to write it that way, okay, and we have basically A naught times 1 plus A naught times 2 alpha delta T, okay, and then we're neglecting that last term because of the alpha squared factor in it, okay. So when we do this, okay, we come up to this point, notice that we can subtract that initial area from both sides of our equation here. And when we do so, we get what we're looking for, which is simply the change in area, okay, due to the thermal expansion, which you can see is just, okay, that coefficient of area expansion is just twice the coefficient of linear expansion, which is what we're asked to prove in this problem. So let's now take a look at some examples, okay, applying this empirical relationship that describes a thermal expansion of materials with changes in temperature. So in our first example, we are talking about a 15-meter long steel girder, okay, used in the construction of buildings, where we're told that the temperature extremes go from minus 20 degrees Celsius to 40 degrees Celsius. How much will the length of that girder change between these extremes? So I think when you think about this, you can see that this is a real engineering concern, okay, in the design of buildings. Obviously, when a building is designed, the expansion of the materials involved in the construction of that building have to be taken into account, okay, as the temperature changes between, let's say, low temperatures in the winter to high temperatures in the summer. So for a given geographical location, estimates have to be made for how much those materials are going to expand, and that has to be taken into account in the design of buildings. So here we will start with our empirical formula stating the linear coefficient of expansion of materials, since we're asked to find the change in the length of this girder. And we need to start by identifying what the girder is made out of so we can get the correct expansion coefficient. So here we're told that this is a steel girder. So the coefficient of linear expansion is 12 times 10 to the negative 6 Celsius degrees to the negative 1. So when we use that, we plug it into the equation. Our initial length for the girder is 15 meters. And the extremes of temperature, the temperature range from minus 20 to 40 is a 60-degree temperature range. When we do the number crunching, we find out that that beam will change in length, okay, 0.0108 meters, okay, which is about a centimeter. So when you think about that, okay, that is a significant change in length, okay, for a 15-meter long beam. I mean, think about it. Your typical building is going to consist of many beams, okay, to have a length much greater than 15 meters. So, the building has got to be designed to account for the expansion and contraction of those materials as the temperature changes. So our next example is a similar example. Here we're talking about the steel main span of the Golden Gate Bridge, okay, which is 1.2 kilometers, 1,280 meters long, and we're told here that an allowance of 1 meter is made for its expansion. Okay, given that, what is the maximum temperature variation the bridge could experience and still be structurally stable? So it may surprise you that on a hot summer day, and we're talking about a fairly mild climate, okay, where the bridge exists, but on a hot summer day, that bridge is going to be somewhere on the order of a meter longer than it would be on a cooler winter day. So here, using the same empirical relationship, we're talking about steel here, so we know, okay, what alpha is. And here, we're given our change in length of 1 meter. We know the initial length of the bridge, 1,280 meters, so we need to solve this for delta t. And when we do so, and we plug in the numbers, okay, we find out that this bridge is designed for a temperature variation of 71 degrees Celsius. And just a note, you've probably noticed this. If you've driven over a large bridge before, you'll notice the clicking underneath your tires as your car moves over those expansion joints. When you look at these expansion joints, you'll see that these fingers from one section of the bridge reach into fingers of another section of the bridge, and there is obvious space where they are allowed to, both expand and contract, okay, to allow for the fact that materials expand and contract as their temperatures change. Now, this final example on thermal expansion is a conceptual example, okay, one that I alluded to in the opening slide to this presentation. So here it is. You're deciding to cook dinner on your first date with your significant other. Your intent is to impress this person with your culinary talents, but when you attempt to open the glass jar of pickled pig's feet, you discover that the metal lid is too tight. Okay, you don't want to have to ask your younger sister to open the jar for you, so you rely on your knowledge of physics to open the jar and ultimately avoid embarrassment. Okay, this is a situation we've all been in, okay, at some point in our life, right? Okay, what can you do to get the lid off Okay, that will certainly impress your date if your physical strength does not. Oh yeah, here, okay, a table of expansion coefficients may help. Okay, so if you don't want me to give you the answer straight up, you're welcome to pause the presentation here and see if you can figure it out. All right, hopefully you figured this out. Take a look at the expansion coefficient for glass as compared to, let's say, metals like iron or steel, what the lid is made out of. And you'll notice that the expansion coefficient of glass is much smaller than for iron or steel. Okay, in other words, much smaller than what it is for the lid of that jar. So in theory, if you could, change the temperature of both of those materials by the same amount, okay, the iron lid is going to expand more than the glass will. So there you have it, folks. This is a trick if you're trying to get that tight lid off the jar. The smaller coefficient of expansion of glass than most metals. Okay, put your jar and lid under hot water. Okay, especially the lid, and allow that lid to expand. Okay, it will expand more than the jar will for the same change in temperature, and you will be able to save the day and get that lid off. Don't follow the advice of Homer Simpson here. All right, so I do apologize. I did a lie on the previous slide. It does turn out that we have one more example that I forgot about. And this example, the unusual behavior of water, is an important example, okay, especially if you happen to be a fish trying to survive in a lake in the wintertime. So let's take a look here. It turns out that most liquids and solids, okay, expand as they experience an increase in temperature, okay, but water appears to be an exception to this rule within the temperature range of 0 degrees Celsius to 4 degrees Celsius. We're asked to use this to explain, okay, how this unusual behavior can account for the fact that lakes freeze from the top down rather than from the bottom up. So let's take a look at this. In the wintertime, as the air temperature drops, and we're talking now about temperatures above 4 degrees Celsius. So as the air temperature drops, the water in contact with the air on the surface cools. As the water cools, it does what we expect. It decreases in volume. Okay, the volume goes down. That causes it to increase in density. Thus it sinks. Remember from our discussion of buoyancy and Archimedes' principle that, okay, when an object, like in this case the water on the surface, is more dense than the water underneath it, okay, it will no longer float, it will sink. And this sinking cooler water sets up what we call convection currents, okay, whereby the cooler water sinks and the warmer water from down below rises, okay, to the surface. Don't worry, we are going to talk about convection in about a week's time in our unit on methods of heat transfer. Okay, but for now, just realize that we get these circulating currents, okay, where the cold water, the more dense water sinks to the bottom and the warmer, less dense water rises to the surface. Now, that's in the temperature range, when we're above 4 degrees Celsius. But once that surface temperature, okay, the air temperature drops to that 4 degrees Celsius point, okay, then, okay, the surface water no longer contracts. Okay, the surface water now expands as it cools. It now becomes less dense than the water below it. This causes the mixing process due to convection to stop. Okay, as that surface water, okay, eventually from 4 degrees down to 0 degrees Celsius is less dense, will stay on the surface, and will now freeze. Okay, so this is why we end up with the ice being on the surface, okay, rather than forming on the bottom of the lake. And that's a really good thing if you happen to be a fish, because, you know, if you're living down there below the lake, okay, yeah, the water is going to be, you know, more dense, but it is going to remain in a liquid state, okay, deep down. So you may get the surface of that lake to freeze, okay, as it cools quicker, and the warmer, okay, more dense water will be at the bottom of the lake, okay, but remain in a liquid state. So the last topic that we're going to introduce in this video is a macroscopic description of an ideal gas. Now, I know it's been a long lecture so far, and this topic may seem somewhat randomly thrown in, but it's a topic which we need to introduce before we're able to talk about kinetic molecular theory, which will give us a microscopic description of gas behavior, and we're going to get to that in about a week. So we need to cover this somewhere. It also is not totally unrelated to the topic of thermal expansion, because as we find out, gases represent one of the many states of matter, and gases do have this tendency to expand, okay, when heated. So not totally unrelated here. I will say this, that our discussion of this topic will be somewhat limited. This is a topic that if you've taken a course in chemistry, you probably spent a significant amount of time dealing with. What we're going to do, since we don't have that amount of time, we're going to kind of cut to the chase here. We're going to end up at the same place, but cut out a lot of the introductory material to save us some of the time, as we'll see. So let's start out here by describing what are these conditions to make a gas be considered an ideal gas. And by the way, you'll see in the lower right hand portion of your screen, okay, a model for an ideal gas. First of all, we'll describe it from a macroscopic point of view. So if you have a gas which is at low pressure, okay, a very low density, then we can make the approximation that that gas is an ideal gas. Okay, so the truth is we never have exactly an ideal gas. It's just a question of how good the approximation can be. But let's say that for a gas that is at a very low pressure, okay, and low density, that gas we can consider to be an ideal gas. Now, from a microscopic point of view, how do we describe an ideal gas? Well, there's a certain set of criteria that must be met. So we'll start by discussing this volume condition. We need to assume that the volume of the gas particles themselves, okay, are insignificant in comparison to the volume of the container they are in. So said another way, the gas is mostly empty space. It occupies a negligible amount of volume. And you can see that if that condition is met, then you would have, you know, a gas that would be at a very low pressure and low density if the actual volume of the particles was much, much less than the volume of the container that they were allowed to move in. Now, when it comes to this, the interparticle force condition, we assume that for an ideal gas, there are no attractive forces between the gas particles. Okay, now, particles, matter, there will always be some degree of attraction between, you know, two particles on a, you know, even if it's just a gravitational attraction, it's very, very small. But when we look at that attraction between particles being extremely small, okay, then we would say that that gas conforms to our model of an ideal gas. Where is this typically met in real life? Well, when you look at the noble gases in the periodic table, okay, helium, neon, krypton, argon, xenon, these gases, because of their very stable structure, do not interact with other gas particles. They do not exert attractive forces on other gas particles. So when we talk about ideal gases and we want to use real gases that approximate them, we very often use those noble gases. Now I want to make a point here that while we say the attractive forces between particles is small, okay, or negligible, this does not mean that particles cannot collide with each other or collide with the walls of the container. Okay, that is not what we mean by an attractive force. So certainly particles can collide with each other. That brings us to the collision condition. We assume that collisions between gas particles, whether a gas particle collides with another gas particle or whether a gas particle collides with a wall of the container, we assume that all collisions are completely elastic, meaning that they conserve kinetic energy in the collision process, that none of their motional or kinetic energy gets converted into heat as a result of the collision. And okay, finally, we will talk about the motion condition. And this is nicely illustrated in the figure, okay, on the screen you see. We assume that these particles are constantly moving, okay, that's what kinetic theory tells us, that the motion is random, okay, there is no preferred direction they are moving, and that they are simply moving in straight lines since that's in accordance with Newton's first law. If they have no attractive forces on each other, okay, then their paths cannot be curved in any way. So they move in straight lines until they collide with the wall or collide with another gas particle. So now that we know what an ideal gas is, okay, how we can describe it, let's talk about an equation of state for the ideal gas. So before we do that, let's talk about what are these thermodynamic variables that will allow us to describe an ideal gas. Now I want to point out these are macroscopic variables. These are properties that can be measured in the laboratory, okay, with instruments. So here they are, okay, the pressure of a gas, okay, it can be measured, the volume of a gas, the number of moles of gas, the temperature of gas, the thermodynamic or Kelvin temperature of the gas. These are all quantities which can be measured in the laboratory, okay, from a macroscopic point of view. Now, the equation of state that describes an ideal gas, and I will say this, if you've taken a course in chemistry, you may recall that you would start out by talking about the relationship between just the pressure and volume of the gas. Okay, that's what you call Boyle's law. Then you might have talked about the relationship between the volume and temperature of the gas. That's what, okay, the chemist Charles discovered, and you would have called that Charles's law. Then maybe you talked about the relationship between the pressure and temperature of the gas. Okay, Gay-Lussac's law. So you talked about these three independent relationships in the beginning, and then you put it all together and came up with your ideal gas law. And you might have thought way back then, hey, why didn't we just start here, since the ideal gas law really contains all of those three other relationships? Well, that's going to be our approach. We're not going to spend the time to talk about all of these other relationships. We're just going to get to the meat and go straight to the ideal gas law. So this equation of state describing an ideal gas from a macroscopic point of view is this. Okay, we'll express the ideal gas law first in terms of this universal gas constant, this thing we call R. Okay, and here it is, PV equals nRT. In other words, the pressure of an ideal gas times its volume is equal to the number of moles of the gas you have times this constant times the thermodynamic temperature. And if you want to express the ideal gas law in terms of the number of particles or the number of molecules you have rather than the number of moles, you can do that, okay, with just a different proportionality constant. So here it takes on the same basic form. The pressure times the volume is equal to big N, which represents the number of particles you have, okay, times this different proportionality constant, Kb, which we call Boltzmann's constant, times the thermodynamic temperature. And you see here that just setting these two equations Since they look very similar to each other, we can easily find, okay, how this universal gas constant R relates to the Boltzmann constant K, okay, by noting here that, okay, n times R must be, little n times R must be equal to big N times K, in which case, okay, the ideal gas constant R is just equal to the number of particles divided by the number of moles, which many of you, okay, hopefully you've had chemistry, you recognize that as Avogadro's number, and sub A, that number 6.02 times 10 to the 23rd. So we see that the ideal gas constant is simply Avogadro's constant, okay, times the Boltzmann constant. And when we plug in the numbers here, okay, we find out that R has this value of about 8.31 joules per mole Kelvin. So let's talk about the relationships between the variables in the ideal gas law. And what I'm hoping, I mean, certainly let me get the ideal gas law up here on the screen. And certainly you can, from your knowledge of mathematics, determine what the relationships are between these variables. But what I'm hoping is that, okay, by looking at an example, you have enough life experience to actually predict what these relationships are, even if you didn't look at the form of the equation. Okay, so I'm just going to give you some examples, and let's think about it a little bit and see if these relationships are entirely predictable. So starting with the relationship between pressure and volume, well, when you look at the form of the equation, you can see that there's an inverse relationship between pressure and volume. Okay, the example I'll give you, how about the toilet plunger? Okay, when you look at a toilet plunger, you can see that the plunger is trapping air inside of it. Okay, and as you push down on the plunger, what are you doing? You're decreasing the volume, okay, but you're going to increase the pressure. And hopefully you're going to increase the pressure enough to unclog, okay, the toilet, okay, or, okay, unclog the face, depending on what you're trying to do. How about the example of a bicycle tire pump? Okay, if you look at the bicycle tire pump, when you push down, okay, on that on the piston in that cylinder, okay, the bicycle tire pump itself, see what's happening, right? You are decreasing the volume of air in there, okay, causing the pressure to go up. What about the relationship between pressure and temperature? Well, you can see from the form of the equation, there's a direct relationship there. Okay, as the temperature increases, the pressure increases. So, and vice versa. Think about this. If you've ever sprayed propellant, okay, from some sort of aerosol can, you'll notice here that when you spray, when the pressure inside of that can goes down through the act of spraying, okay, you may notice that the outside of the can gets very cold. Okay, as you decrease the pressure, you get a corresponding decrease in temperature. Okay, the relationship between volume and temperature, okay, from the form of the equation, you can also see that that's a direct relationship. The example I'll give you is, how about the piston inside of an internal combustion engine cylinder? Okay, when you look at that, when the gas is combusted in there, you have a dramatic increase in temperature, and that increase in temperature causes a corresponding increase in volume. Okay, as temperature goes up, the volume goes up. You get this expansion, and that can end up doing work. Okay. Relationship between pressure and number of moles, okay, the amount of gas you've got, okay, the equation once again predicts a direct relationship there. How about looking at the example of the air compressor used to fill a car tire? Okay, well, certainly when you look at the functioning of the compressor is actually taking in air from the outside. Okay, so it is forcing air into the tire. So you're increasing the amount of the gas, the amount of air, that causes a pressure increase. Okay, and certainly here, as you can see, this poor man finds out that, okay, using that compressor to add more air to the tire causes an increase in the pressure of the tire. Okay, relationship between the volume and the amount of gas. Okay, also a direct relationship. Okay, example I'll give you, filling a balloon. Okay, so as you blow air into a balloon, you are adding air, okay, you are adding gas, increasing the number of moles, and certainly what happens to the balloon? Its volume increases. Okay, no surprise there. So here we are going to demonstrate the fire syringe. The fire syringe is a cylinder that is fitted with a piston, and inside of the cylinder is some cellulose, some paper. And here's a case where multiple gas variables are going to change simultaneously. So when the piston is compressed, when it's pushed down, the volume of that cylinder, okay, the volume of the air in there is going to greatly decrease. This is going to cause both a pressure increase within the cylinder as well as a temperature increase. And the temperature increase is going to be enough, okay, to reach Fahrenheit 451, which is the ignition point of paper. So let's take a look. So we'll now look at a couple of examples applying the ideal gas equation, this equation of state, in one form or another. And in this first example, this is what I call a single state example, where we're given information, okay, about a gas that we can consider to be an ideal gas that is in one state. And in order to solve a problem like that, if you look at the ideal gas law, okay, with its four variables, pressure, volume, okay, number of moles, and temperature, or number of particles, okay, and temperature, you're going to have to know information about three of those four quantities. So this is an example of a single state problem. And here we're told that in state-of-the-art vacuum systems, pressure as low as 10 to the minus 9 pascals are being attained. Calculate the number of molecules in a 1 cubic meter vessel at this pressure if the temperature is 27 degrees Celsius. So one of the things you've got to really watch out for in these problems is units. Remember that your proportionality constant in the equation of state, whether you're using R for the ideal gas constant or K, the Boltzmann constant, are unit specific. So you got to make sure that whatever units you're using for that gas constant, that all of your other quantities are expressed in terms of those same units. So here, always start any problem by, looking at those macroscopic variables and writing down what you know and what you're trying to find out. So here we've got, pressure, volume, temperature, in this case, number of particles. The pressure is given to us. We'll write that down as in units of pascals. That is an MKS unit. The volume is given to us. It's a 1 cubic meter vessel. That also is in MKS units. The temperature, remember, must be expressed as a thermodynamic temperature in units of Kelvin. Okay, that is a common mistake, and very often it will not be given to you in Kelvin temperature units in the problem. You'll have to make that conversion. So here, 27 degrees Celsius, we'll add 273 to convert that to a Kelvin temperature. Here, we're asked to find the number of particles, not the number of moles. So we're trying to find big N. So we will use the equation of state expressed in terms of Boltzmann's constant, PV equals N times Boltzmann constant times the thermodynamic temperature. We'll solve it for N. And then it's just a matter of plugging in our numbers here with our units. Other than converting Celsius into Kelvin, all the other units are acceptable. They are, MKS units. and we do the calculations here, and we find out that our number of particles is 2.42 times 10 to the 11, which, if we want to convert that into moles, is 4 times 10 to the minus 13 moles. So this last example we'll take a look at involves what I would call a comparison of two states. So this is another common type of problem. Whereas the previous problem involved an ideal gas in a single state, this is the type of problem where you have a gas, starting out in some given state, and you make some sort of change to it, some sort of change in terms of these macroscopic variables. That is, you change, the volume, the pressure, the temperature, the number of moles or the amount of gas. You may change a single quantity, or you may change multiple quantities, and you're asked to find out how the effect of these changes, what effect does it have on some other state variable. So here, we're told that a certain flexible weather balloon, it contains helium gas. Initially, the balloon is at sea level at a temperature of 25 degrees Celsius and a barometric pressure of 720 torr. The balloon then rises to an altitude of 6,000 feet. So you see that's where the change is made. And when when the balloon changes altitude, this also creates a change in pressure to 605 torr and a change in temperature to 15 degrees Celsius. We're asked to determine the change in volume of the balloon as it ascends. Notice here that in this problem, the mass of the, or the number of moles of the helium, the amount of gas we have, is not given to us. But we'll see that very often in these comparison problems where you're comparing one state to another, that's okay. There can be information you don't have, because if you don't know what the value is of that variable, as long as it's the same value in both the initial and final state, it doesn't matter that you don't know what that value is, when we make that comparison. So let's start out, as we did in the previous problem, by identifying what each of these variables is: pressure, volume, temperature, amount of gas, for both the initial state and the final state. The initial state of the gas at sea level versus a final state at 6,000 feet. So we have to read through the problem, make sure to pay attention to units as always. And we're told here that at sea level, the temperature starts out at 25 degrees Celsius. We got to convert that to Kelvin. But at a height of 6,000 feet, the temperature changes. It drops 10 degrees Celsius and 10 degrees Kelvin. From 298 to 288. In terms of the volume, here's what I was saying. We don't know what that volume is, in the problem. That's what we're trying to find. If it has an initial volume, I'll say VI, V initial. Its final volume, V final, is going to be unknown to us, but it's not the absolute volume that we're asked to find. It's simply the change in volume. So again, a comparison of these two states is all that's required in the problem. When it comes to pressure, we're given both the initial pressure of 720 torr. Remember, there's 760 torr in 1 atmosphere. We've got to make the conversion here to our MKS unit of pascals. So we do that conversion. And at 6,000 feet, the pressure drops to only 605 torr, or 8.06 times 10 to the 4th pascals. Once again, we had to do that conversion. In terms of the mass, the number of moles or the number of particles here, we don't know what that is, but our balloon, regardless of what altitude it's at, has the same amount of gas. It is a closed system. The amount of gas doesn't change. So once again, although we don't know what that amount is, it will not matter because it does not change in the problem. So we need to decide which form of the equation of state we want to use. And here we will once again use it expressed in terms of Boltzmann's constant. Okay. I say that because Boltzmann's constant is it is a in SI units. We could have just as easily done this using the universal gas constant expressed, okay, in SI units as well. It really doesn't matter, because whether we're talking about the number of particles or the number of moles, that is a quantity that will cancel out. So like I say, you could just as easily solve this problem using the ideal gas law in terms of the ideal gas constant as well. Okay, but we'll choose to do this. So when we solve this for Boltzmann's constant here, okay, we can write this in a form that compares the two states, right? That the pressure times the volume divided by the number of moles divided by the temperature is equal to a constant, and that constant must be the same for both the initial state of the gas and as well as the final state of the gas. So this is what our equation will look like for a comparison of states. For our problem, the number of particles of gas doesn't change. It's a closed system, so that will cancel out from both sides of the equation. So we can write it like this. Sometimes this is called the combined gas law, okay, where we have a fixed amount of gas, so that the amount of gas is no longer a variable in the problem, okay, just the pressure, volume, and temperature. So taking this and plugging in our quantities here, okay, from our matrix above here, just plugging this in, we see that we don't have either the initial volume or the final volume, but we can express one in terms of the other. So doing the number crunching here, we find out that our final volume is 1.15 times our initial volume. So you can see here that as a balloon rises to that new altitude, okay, it experiences a drop in temperature, okay, a drop in pressure, okay, but in this case the volume increases slightly.